Welcome to Chapter 10, the third screencast dealing with liquids, solids, and intermolecular forces. Some other properties of liquids that we haven't talked about in the previous screencasts are things like viscosity, which is the measure of a liquid's resistance to flow. Things like cough syrup or pancake syrup or motor oil have a high viscosity. They don't flow very easily. They're kind of thick substances, whereas things like gasoline or, for that matter, water or ethanol have a much lower viscosity. They flow much more readily. Another property is something you've seen when you've seen water droplets bead up on a waxed car or on a granite countertop, and that is something called surface tension, which is the resistance of a liquid to spreading out. And when the liquid spreads out, it increases its surface area, and things that tend to not spread out, that tend to stick together in little beads of the liquid, have a high surface tension. So water has a high surface tension. It forms droplets. So does the liquid metal mercury. And surface tension is a property that allows things like water bugs to be able to walk on the surface of water. And part of it is they are not very massive, but part of it is that water makes kind of a little skin essentially over it due to the surface tension, the attractions between its molecules. And one thing that viscosity and surface tension have in common, although there's some differences between the two, is that both properties are usually higher in substances that have larger intermolecular forces. Now note that flowing and beating up are different properties, and so the intermolecular forces being larger will vary from substance to substance. Molecules that don't maybe have that strong intermolecular forces but are tangly molecules will tend to be more viscous, not flow as readily, and things that have strong intermolecular forces will tend to have a higher surface tension kind of regardless. So note there are some differences between the two. And sticking with surface tension for just a little bit more, if we look at some molecules of a substance in a liquid form, and here's the surface of the liquid, notice that in the interior of the liquid, a given molecule is attracted by all the molecules nearby, whereas a molecule on the surface is attracted by molecules on the sides and below it, but there are no molecules on the top of it to attract. And what this means is that on the surface, the molecules sort of feel an attractive force only on one side, and they tend to be drawn in towards the middle of the liquid. Whereas molecules or atoms in the middle of the liquid are attracted equally in all directions. And so in terms of kind of a shorthand, how this is on your handout, molecules at the surface have unbalanced attractions. Molecules in the middle of the liquid or in the interior have balanced attractions, and the unbalanced attractions at the surface is what pulls the surface molecules sort of inward and tends to form beads and makes a sort of a skin that the water bugs, for example, if the liquid is water, can walk on the top of. So here are a couple examples. Here are small beads of water forming on a blade of, looks like grass. And here is a meniscus that's upward, concave upward, for mercury. And here is the water meniscus concave downward. And note that these are both substances, water and mercury, that have strong attractions between their molecules in the case of water and atoms in the case of mercury, but they make either a downward or upward meniscus based upon differing attractions between the molecules of the substance within itself, their cohesive forces, and the molecules and glass, which is their adhesive forces. And so water molecules attract glass much more strongly, whereas mercury atoms only attract each other, and they really are not attracted by the glass at all. Here's a table of some viscosities and surface tension values for some common substances. And notice the somewhat different units: Newton seconds per meter squared for viscosity and joules per meter squared for surface tension. And here are our substances. And notice things like glycerol, which has 3 different OH groups that are capable of hydrogen bonding, so strong attractions, and also many groups that can kind of tangle as they try to flow by. Very high viscosity, so it's somewhat intermolecular forces but somewhat shape of molecule. And then these are a number of substances that have not too wildly varying surface tension, but notice water very high and glycerol very high, as well as ethanol to some extent, and mercury is in its own category. And these are largely due to hydrogen bonding attractions being particularly strong. Now, another example is DNA, which surely you've heard of before. It has this famous double helix structure, and DNA, the double helix structure, it's the basis for life. It's how our genetic information is passed on from parent to child. And the double helix consists of phosphate and sugar units that are connected to one of 4 bases: adenine, cytosine, guanine, or thymine. And then there's a helix or ribbon of 1 and another helix or ribbon of these groupings, and then they are attracted from one side to the other via hydrogen bonding. So the S and P here represent sugar and phosphate groups, which kind of makes the backbone. And now the C, G, A, and T represent cytosine, guanine, adenine, and thymine, respectively. And notice that thymine and adenine have a nice hydrogen bond and a second one, whereas cytosine and guanine have 1, 2, 3 locations where they hydrogen bond. So the structures show why cytosine always pairs with guanine and thymine always pairs with adenine, and the hydrogen bonds being very strong intermolecular attractions but not as strong as regular bonds explain why these molecules can separate from each other relatively easily when reproduction occurs or when duplication occurs. And so we have a chain of what are called nucleotides, where we have a phosphate group, a sugar, and then either thymine or adenine or cytosine or guanine. This is one strand of DNA. There will be a parallel strand here matching. Adenine will have a thymine across from it. Thymine will have an adenine across from it. Guanine has cytosine, and cytosine has guanine, and they match up just nicely with strong hydrogen bonding, and that is what holds the strands together. So, summary here for your handout: the 2 strands of DNA are held together by hydrogen bonding. 2 hydrogen bonds between thymine and adenine, 3 hydrogen bonds between cytosine and guanine. So hydrogen bonding is very, very strongly responsible for life itself, if you will. Now, a couple more examples of substances and their types of intermolecular forces and characteristics. Here is a series of somewhat similar compounds, all carbon-hydrogen compounds: CH4, which is methane; C2H6, which is ethane; C3H8, which is propane. Then maybe you can see the pattern. 4 carbons will have 10 hydrogens, and that is butane. 5 carbons will have 12 hydrogens, and that is pentane, and the trend keeps on going, twice as many hydrogens as carbons plus 2 more, and these are substances known as alkanes. And just as a little bit of a test, what would be true about alkanes? So you might want to think about whether they're all going to be polar, all going to be nonpolar, some of each, or both. And before the answer is revealed, note that they're all carbon-hydrogen compounds. And so if you think about it, hopefully you'll say, oh, these are all nonpolar substances because carbon and hydrogen only have a small electronegativity difference of 0.4. They tend to cancel out because of their symmetry. And so all of what are known as alkanes are nonpolar. They have only London dispersion attractions, and their boiling points, their melting points, their other things that measure strength of intermolecular attractions will increase as the size of the molecule increases. And this is very important in things like how we get the substances that come from crude oil. So crude oil is a mixture of hydrocarbons. You heat it up, pump it through a furnace, it gets hot, and run it into what's called a fractionating tower. It's basically a distillation, but with many, many sort of repetitive stages. And the molecules that make up this crude oil mixture get separated on the basis of different boiling points. So the very small molecules that boil at a low temperature will not condense until they're near the top of the column where it's cooler, and they can be drawn off. Gasoline, which tends to have maybe 5, 6, 7, 8 carbons in its chain, will have somewhat higher boiling points and will be drawn off a little lower in the column. Kerosene, 10, 12 or more carbons, bigger molecules yet, will have to be at a higher temperature before they will be condensing and drawn off, and then keep on going. Heating oil, bigger molecules yet, lubricating oil, larger, and asphalt and things like that are going to be solids at any kind of reasonable normal temperatures for us, are going to be a lot bigger molecules, stronger intermolecular attractions, and they won't melt until you get much, much higher temperatures. And one more example before we end this screencast is compounds that look pretty similar to alkanes, except instead of 4 hydrogens, there's 3 hydrogens in an OH group for the first carbon. And then instead of 6 hydrogens, there's 5 hydrogens in an OH group. So basically, for all of the alkanes, we just have one of the hydrogens being replaced by an OH group. And the compounds here are methanol, ethanol, propanol, butanol, pentanol, etc. These are what are collectively called the alcohols. And one more question for you here. What's true about alcohols? So think about whether they're polar or nonpolar, or have London dispersion forces, or dipole-dipole attractions, or hydrogen bonding, or polar and nonpolar regions. And if you think about it a little bit, hopefully you will say there's an awful lot of these that are true. They are polar. The OH group is polar. All molecules have London dispersion forces. Polar groups, the OH group, is a dipole-dipole attraction. It's just an extra strong one that's called hydrogen bonding, so it has that. And they do have polar and nonpolar regions. The carbon-hydrogen part is nonpolar, and the OH region is polar. So as a summary for that, they're all polar. They all have London dispersion and hydrogen bonding attractions, and the boiling point will go up as the size of the molecule increases, and or if there are more OH groups. So that's it for this screencast. Stay tuned for the next one coming up soon.